All right, so let's start with page 284. We're going to talk about acid catalyzed hydrolysis. And this is something you want to include in your reactions. We're going to talk about decarboxylation reactions. And these are really going to apply to the beta keto esters. So the one that we've been looking at was the acetic acid, well, ester. So we've been doing this reaction earlier, yesterday. And so when you use like sodium methoxide and you put an R group on there, so you have an R group, so you'll want a primary alkyl halide, okay? You make your enolate, and then that enolate will attack the R group, and you get your alpha substituted alkylated product here, where the R group's there. Now, what you're going to learn on this page, page 284, is that when you take this and you treat it with acid, you can hydrolyze the ester to the carboxylic acid. And then when you have a beta keto acid, it will undergo decarboxylation. So you're going to lose this whole group here. Okay, so you're going to lose this whole group. And we're going to see what that looks like, okay? So that's the whole point of this. So number 7, it says esters can undergo acid catalyzed hydrolysis as shown below. So here we have the methyl ester, and we're adding acid. All right, and then that gives you the carboxylic acid plus methanol. So what are the products of the acid catalyzed hydrolysis? So basically the carboxylic acid and the methanol. And this is the same thing if you go this way, it's Fischer esterification. Carboxylic acid, alcohol, and a acid, right? So this is the same thing as Fischer esterification. All right, so now we're on 7B. Acetoacetic ester and malonic ester so this is your malonic ester, and this is your acetoacetic ester. So these products then can undergo acid hydrolysis. And so what are those products? There's your carboxylic acid. And then this hydrolyzes, the malonic ester hydrolyzes on both sides, okay? And so there you do, but this does a decarboxylation, both of these. And so you're going to lose the carboxylic acid. And here you're going to lose 1, okay? So then if you draw your product here, and we'll show you the mechanism. This would be a ketone, is your product, and this one would be an R substituted carboxylic acid. So if you get a carboxylic acid, the ketone. Okay, so let's just go ahead before we do the mechanism and do C. Number each of the carboxylic acid products in 7B where the carboxylic acid carbon is number 1. So this is the relationship between the carbonyl groups is what? So if this is number 1, that's number 3. Over here, that's number 1, that's number 3. So the carbonyl groups are a 1-3 relationship. And that's a beta. Okay, so that's the beta keto or a beta carbonyl, carboxylic acid. And those are the ones that undergo decarboxylation. Okay, I put a star by D. Carboxylic acids can undergo decarboxylation when a second carbonyl group is located at the, what did you say? The 3 position. That's right. Draw the decarboxylation products for each of the compounds shown in 7B. Okay, so that's this one here. Make sure you have those. After decarboxylation, the acetoacetic ester synthesis leads to the formation of what? Ketone. After decarboxylation, the malonic ester synthesis leads to the formation of what? Carboxylic acid. Okay, turn the page to 285. We have model 3, and that's our last model, folks. Okay, so let's see if we can get model 3 so you can do your additional problems. I did promise you that I would do the mechanism, so let me do the mechanism here. See if we. Okay, so at this point I want to show you the mechanism for the decarboxylation reaction. And when you do this, you want to be just concerned about how you draw the, so this is your acetoester, and you want to draw your acid like this, okay? So when you draw your beta keto acid, drawing your lone pairs, and this makes a 1, 2, 3, 4, 5, 6-membered ring. If you kind of look at that as a ring, and what happens is this OH, those electrons are going to go here, and then these electrons go here, and then this goes here, okay? And so when you do this, then your number 3 carbonyl picks up that hydrogen from the carboxylic acid, and you now have this bond here, we'll make blue, goes here, and then the carbon goes like that, right? So there's your CO2, the decarboxylation, and you'll see that this product is an enol. And enols, we understand, tautomerize. And so I just do it quick and easy like this, and you see that you have, that is your ketone. And that is the product of a decarboxylation reaction with the acetoacetic ester synthesis. All right, so now we're on to model 3. And model 3 will not be on today's quiz, okay? But you'll have to know it for Quizam 4. So if I were you, I would get out another reaction sheet and include this one. This is model 3. This is called Conjugate Addition. We probably still have another 3 or 4 reactions to learn in this chapter. This is also called 1,4 addition. So Michael, it's called Conjugate Addition, which is a 1,4 addition. You've seen a little bit of conjugate additions before. And this is also called the Michael addition reaction. Now, the starting material for this reaction is the product of an aldol reaction. So what's the product of your aldol reaction? Alpha, beta, unsaturated ketone. Okay, so on your reaction sheet, the starting material is an alpha, beta, unsaturated ketone. And then you're going to add a nucleophile. So this alpha, beta, unsaturated ketone is the electrophile. So let's look at this. Alpha, beta, unsaturated ketone. And then you add a nucleophile. And notice the nucleophile has added at the beta position. This is the 1,4 addition. And we know that that's the thermodynamic product. And then the kinetic product would be as if it added the 1,2. Okay, this is the kinetic. And you'll find that certain nucleophiles will go 1,2. Other nucleophiles go 1,4. 1,4 nucleophiles tend to be what we call soft nucleophiles. Those are going to be copper. Kinetic are hard. And those are going to be your group 1 and 2. They're like magnesium. Like Grignards are hard. Lithium is hard. Copper is soft. Sulfurs are soft. These are big. Soft is like a high polarizable, kind of big fluffy electron cloud. And like metals, like gold and palladium, your transition metals that like to form carbon bonds, those are considered soft. Okay, and they prefer a 1,4 addition. All right, so let's read our problems. Consider the conjugate addition, 1,4 addition reaction shown in Model 3. What is an alternate name for this conjugate addition? Okay, so I think we already said that, right? I'll just highlight it. The Michael addition reaction. Okay. Explain why the starting material is called an alpha beta unsaturated ketone. Well, there's your alpha. And there's your beta. So you have a double bond between the alpha and the beta position next to the ketone. The atoms involved in conjugate addition are numbered 1 through 4 as shown in Model 3. What position number does the nucleophile add to form the 1,4? So notice this is numbered 1, 2, 3, 4. And the nucleophile added to the 4 position. What position does the nucleophile add to form the 1, 2? So 1, 2, 3, 4, and the nucleophile added to the 1, 2. So the 2 position. The thermodynamic product is the 1, 4. The thermodynamic product is the more stable product. It's always going to be the more stable, okay? Thermodynamic, more stable. So in an energy diagram chart, it would be lower energy. Draw 2 resonance forms for the alpha beta unsaturated ketone below. Okay, so let's do number 9A. One, 2, 3, 4. Draw in your lone pairs. So these electrons can go here and here. Okay, see how it's overall neutral? In the resin structures drawn above, where do the positive charges occur? The positive charge is at carbon number 4. Okay, if you were to do the one where you had it at the 2, you would just move one of these, okay? So if you just moved one here, you would get that. So that's positive charge is at carbon number 2. The alpha beta unsaturated ketone acts as a, see the positive? So it acts as an electrophile, okay? Now we're on page 286, question number 10A. The choice of the nucleophile determines whether the 1,4 addition or the 1,2 addition occurs. Remember I told you that soft nucleophiles prefer the 1,4 addition. That's what we're talking about here. Hard nucleophiles will do the 1,2 addition. So nucleophiles that are stabilized, less reactive, will afford a 1,4. So stabilized. Circle the nucleophiles below that are considered stabilized. Okay. Soft are carbon-carbon bonds. Okay. So this enolates are considered soft. Okay. These are soft. So circle that one. Phenyl, magnesium bromide. Magnesium is group 2 metal. Okay, these are considered hard. Hard, they're like a baseball. I think of them as size. They're just really small baseball. Soft, you think of a softball. Okay. Copper. Copper would be soft. I'm going to put that over here. Phenyl to copper, lithium. This is a cuprate. Copper forms multiple charges here. This basically delivers you a phenyl nucleophile. It reacts just like the Grignard. It gives the negative, but it makes it soft. Okay. The other one that's going to be soft is this enolate ester. So enolates are going to be soft. And then you got another, you got to look that it's on the carbon. Okay, so if it's carbon, it's soft. So enolates are soft. Nucleophiles, so 10B, you circle. Yes, so nucleophiles donate electrons. The nucleophile would act as the Michael donor. Okay, so the 1,4 is an acceptor. So this is the nucleophile is the donor. The electrophile would act as the Michael acceptor. 11. Label the starting materials in the reaction shown below as either a Michael donor or a Michael acceptor. All right, so let's draw this out. For 11A, number 1, 2, 3, 4, you should always number those. Your alpha, beta, unsaturated ketone. You should also practice how to make that. And this is an enolate. Okay, so it's obviously going to do a 1,4 addition. And since it's your nucleophile, it's going to be a donor. So Michael donor. This is your electrophile. This is going to be a Michael acceptor. And so you see that those electrons there go there. These electrons push up. These electrons push up. You do need to know this mechanism. And you've added to the 4. So here we have 1, 2, 3, 4. And this carbon's here. CO2, CO2. All right. And then this is going to actually pick up a hydrogen. Okay. So it picks up a hydrogen from the solvent. And so then we have a hydrogen here. We have our double bond there. And then we have this CO2, CO2. Now, what's interesting here is, yes, that's an enol, and it is going to go tautomerize. So tautomerization. And I just do it quick and easy here. All right. So then your product becomes this molecule here. Let's see. Oh, we lost our other carbon here, didn't we? Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there we go. Okay, so 11B. We're almost there, folks. Hang in there. How is malonic ester converted to the anion shown in 11A? So how do you convert this to the anion? So the Michael donor. So that is malonic acid, ester. Okay. And you would just use sodium ethoxide. And there's your alpha carbon. And you would just deprotonate that hydrogen, and that would give you your enolate. So you should know how to do that. We'll just put the little enolate, which looks like a monkey face, on there. All right, and do you see that this is the same as this, the Michael donor? So that's, see above, draw curved arrows, we did that. All right, folks, we're down to our last question, number 12. So number 12, draw the products for each of the following Michael addition reactions. Recall that H3O plus and heat result in hydrolysis and decarboxylation. All right, so we have this alpha beta unsaturated ketone. Now, just for fun, how would you make that? That would be alpha beta. So retrosynthesis, right? That would be, there's your 2, that's your alpha. And then you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that would be what? That would be your aldehyde, right? So 1, 2, 3, 4, 5, 6. So basically sodium hydroxide, and you make your enolate from your alpha carbon. This is an intramolecular reaction. And then this would come here and form this right here. That would get protonated, right? That would get protonated to make your beta hydroxy, and then heat would make, you would lose the water. So you would lose the water to make that product. Okay, so that's how you make that. Now this is a Michael acceptor. So you want to go ahead and number 1, 2, 3, 4. and you have an excellent Michael donor, the phenyl copper lithium, and then you treat it with water, okay? The water will protonate the enol, and it undergoes enol tautomerization. So this is going to add to the 4. It's going to look like this, okay? And I'm actually going to draw the phenyl out. Okay, so there's your phenyl, and then the water. This picks up the water. And then you can do tautomerization. And you see that that gives you the phenyl adding to the number 4 carbon to give you the product. Okay, B, let's do B on page 287. All right, so we have our alpha beta unsaturated ketone, and we're reacting it with this, which is, this is an acetoacidic ester. We first react with sodium ethoxide, which is a good match here because we have that. And this is going to make the enolate. So if you draw in your hydrogens here, this will make your enolate. That's the first thing that'll happen. Okay, so there's your alpha carbon, there's your enolate. And then the second thing, this will add to the Michael acceptor. This is our donor, the carbon nucleophile. 1, 2, 3, 4. So it's going to add to the 4. We show that here. Okay. One, 2, 3, 4. On the 4 position, we're adding this carbon here. And then we have 1, 2, and then we have this. And then we check carbons. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And then, of course, this would pretty much pick up water, and then it would undergo enol tautomerization. So I will just go ahead and draw that. Okay, and then we count carbons. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. All right, and the next thing we do is we add H3O plus and heat. So we have a beta keto ester. So what's going to happen is we're going to get some decarboxylation, so of the ester. So all of this that I highlighted will decarboxylate. So let's do that. I will first show the hydrolysis to the carboxylic acid. Okay, I'm also going to check carbons. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then this decarboxylates minus CO2, and then we can redraw that. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3. 1, 2, 3. 1, 2. Here's our carbonyl. 1, 2, 3, 4. 1, 2, 3, 4. And then on the alpha, you have the CH3 here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. and that is your product, okay, after decarboxylation. All right, now you have your additional problems. Remember to draw these out. Looks like you're doing, make sure on 13 you label your alpha and your beta and you draw your line, and then you can draw your synthons and your starting material. The number 14, you need to draw out the reaction mechanisms, okay? And then 15, you need to draw out the reaction mechanism again, okay? And those are your POGL exercises due this week. And tomorrow I will present some reactions in chapter 22 that you need to focus on in your textbook.